Now that we've seen how different factors affect the spread of disease, the next logical step is to see if we can make prediction into the future so that we can now say, okay, yeah, this is what we expect the total number of cases to be by the end of this pandemic. This is when so and so country will exit, the pandemic. So my interest, of course, is for Nigeria. But I came across this nice piece of work done by Joshua McD. So the guy's done really good work. So you can just download this and then run for Nigeria so that you can see what the future looks like. So that's what I'm going to do right now. So you pass the first argument, Nigeria, then you set print to on, and then you run. So here the result is out. So let us analyze what the results, is for Nigeria. We know that we have some tons of parameters that affect, the SIR model, which predict the spread of diseases. So here we are looking at the contact rates, we're looking at the removal rates, we're looking at the population size, the initial infection, so the final number of cases, and then the number of susceptible, and then we can see what the daily forecast is. So we're going to talk about how these calculations were performed. But first, just look at the results. So there is this website that has this data of, as the daily cases has been reported and it's been updated. So to perform this calculation, this algorithm actually took the data from that web page. The most recent, the latest update of that data. All right. So for Nigeria, we've been 22 days into this pandemic. The outbreak was reported on 9th of March. So the start of acceleration is 25th of March. That is when the rate of cases reported daily started accelerating. All right. So the turning point is expected to be 2nd of April. That is when it will stop accelerating. Accelerating doesn't mean increasing. What I mean by accelerating means that it's the rates of change of the rate of change. That is the second derivative. So, which means that the number of cases we have will still be increasing, but the rate of change of the number of cases of the rate of change will be reducing. That is at this on this part. So here we'll be here by 2nd of April. So that is the point of inflection. So then the start of steady growth rates when it becomes linear will be by 11th of April. Then we'll enter the ending phase by 28th of April. So in total, we expect about 369 people to be infected. There'll be 1,333 and 36 people that will be susceptible. So if you add these two guys together, you should come to this value. All right. So the for today, 30th of March, we expect about 17 new cases to be reported. So, but by 1st of May, we should be, in the ending phase. So, the for us to have confidence in this data, we see that the p-value is 10^-18, and we need a really really small value to show that you cannot just come up with these statistics that you use for this prediction by random guess. So now that is that for the analysis of the data. Now let us now think about how this algorithm was developed. The idea is simple. You have a differential equation that models the spread of disease, and it has the parameters, and those parameters, they are actually unknown. You have to compute what those parameters are for different countries. So the only thing that you have is the data that's being reported from those countries. So let us say you make a guess of those parameters and then run the calculation. You'll find out that your results will be different from the reported values from those countries. So what you are now trying to do is to try to minimize the difference between the results and then use that to estimate the parameters. All right. So now to do that, the idea is simple. So you first program the differential equation, and then here this is the differential equation. It's really a simple model. All right. So that program the rate of cases per day, dc dt. Now, but it has some parameters that it needs. All right. And the parameter that it needs for that calculation are this beta, the gamma, the n, and the IU is the number of infection, the total number of population. This is not the population of that country, all right? So, but this is the population that is likely to be infected, and then those that are already infected. So then you have the gamma, which is the rate of removal, which is depends on how effective the government is at quarantining those who are already infected. And then you have the beta, which has measure of contacts between the infected people and those that are not that are not infected. So now the result that comes from that calculation, all right, now is being compared with the actual reported data from that country. So the number of cases reported from Nigeria in this case will be is the C. Then the C sol is what comes from the SIR model. So we take the difference that we're trying to minimize. Then also the number of new cases that is being reported per day, we also take that from Nigeria, and also the difference, I mean, day to day from the differential equation. Now, if you look at the solution of the differential equation here, we're actually passing T-span. This T-span is 0 to length of C minus 1. That is the total number of days that Nigeria has been in the pandemic. That is what we're using here. So, and then in case the ODE server experienced a problem and then it exited, so we have to be sure that the length of T-sol is equal to the length of T-span. That is the number of time, the days that we have been in the pandemic, and the number of prediction that comes from the ODE server is actually the same. All right. So now, so if that, I mean, is done, then this difference that we measure here will now be sent to the F-mean search to search for the parameters that will actually fit that model. That is using the F-mean search. All right. But we need an initial guess BO. This BO is sent in here. And this BO was calculated using an initial guess function, which is here. So this guy here returns the BO. So that BO was sent here and then used to get the actual parameter. So when you now get the actual parameter, you now start making prediction, calculating the endpoint, calculating the point of inflection, and then forecasting into the future. So the you have about 800 lines of code here, but the most of the calculation were done in about 250 lines of code. So basically, we use the ODE function, the initial guess, the difference estimator, and then the parameter estimator. And then from there, then you cannot make any other kind of prediction that you want to make. So thank you for listening.